In this video, we're going to see some applications of differentiations. The graph is a nice way, an intuitive way to study functions. So for example, given the graph of a function y equal fx, then it is very easy to see which part of the graph is decreasing or which part of the graph is increasing. Since we are learning about differentiation, we may ask whether the differentiation actually have something to do with this property decreasing or increasing of a graph. Then we may also care about points across which the graph of the function actually changing directions, for example from decreasing to increasing or vice versa from increasing to decreasing. And what does the derivative of the function has anything to do with these changing points? And also based on the graph, you might see that there are parts of the graph that actually looks like a parabola that's open down, and there are also parts of the graph that actually looks like a parabola that open up. These are what we call concavity of the graph, and then of course we can also care about points across which the concavity change. Now in general, you do not get the nice graph like this. You only get very often you only get a function via its algebraic formula. Like for example, in this example, you see that fx is equal to x power 4 minus 4 times x power 3 plus 11, and you do not have an immediate graph of this function, so you cannot easily say about the decreasing or increasing property of f, as well as the concavity of f, inflection points, etc., like we seen earlier in the slide. So we may ask, how can we deduce all of this property just based on an algebraic formula like this? And fortunately, actually, we can actually do that. So for decreasing or increasing property of a function, so the following theorem actually is very useful. So for function f, if we can compute the derivative of f on an open interval I, and we know that the derivative of f at x is positive for all x in this open interval, then we can conclude that f is increasing over I. And if we know that the derivative also exists on an open interval I and are negative on that open interval, then f is actually decreasing over I. Now the derivative of a function, for derivative of a function we actually have three possibilities. So the first thing is that it is not zero. It is defined and it's not zero. The second possibility is that it is actually zero, and the last one is that the derivatives do not exist. So because when the derivatives of f is not zero, it can help us to know about the decreasing or increasing property of the function f, then it is natural to distinguish this case with the other two cases. And for this, we call a critical value of a function f any number c in the domain of f for which the derivative does not exist, or the derivative of f at this point exists and is zero. Now remember that the derivative of f as I equals c is zero, meaning that the tangent line to the graph at the point with coordinates c and fc is actually a horizontal line. Then we can actually rephrase the definition of critical values like this, meaning that a critical value of f is any number c in the domain of f for which the derivative does not exist, or for which the tangent line at the point with coordinates C and FC is horizontal. The following diagram actually gives us a nice idea of what is a critical value. So in this picture we see that C1, C2 and C3 are critical values for which the derivatives exist and is 0, and C4 and C5 are actually critical values for which the derivatives does not exist. Now also from this picture we might see that the critical values actually have some special properties. So actually let's look at 3 points that we already make bold for with x coordinates C2, C3 and C4. So in this case, locally, we see that these points are actually at the highest or lowest position, locally, I mean. And these points are actually called relative extreme points. And if we want to distinguish highest or lowest position, then now we actually have what we call relative minima. A relative minimum is actually the y coordinates of a relative extreme points for which the corresponding point stay at the lowest position locally in the graph. So see for example FC2 and FC4 actually are the smallest number locally when we consider the function only on a small open interval. And for the rest, for the remaining points, the value of FC3 in this case is actually the greatest value of f if we consider f only on a small open interval. So for this reason we call f of C3 a relative maximum. And in this case we can easily see that f of C4 is not only a relative minimum, it's actually an absolute minimum, meaning that the value of f of C4 is the smallest value that f can get. So for now we already have the notions of relative extreme points divided into 2 cases, a relative maxima or relative minima, and we might also talk about absolute minimum or absolute maximum. Okay, so that's an intuitive way to see through these new notions, but actually we can have a rigorous way to define them. Let I be the domain of the function f, then we say that fc is a relative minimum if there exists within I an open interval I1 containing c such that the value of f of c is less than the value of f of x4 on x belonging to I1. And if f of c is less than f of x4 or x in the domain of f, then f of c is actually called an absolute minimum of f. And now similarly, if we reverse the inequalities, then we have the definition of relative maximum and also the definition of absolute maximum. And actually relative minimum or relative maximum is called in general a relative extreme value. From the earlier example we can actually see that the relative extreme value only occurs at critical values, and this is actually a general fact. And that is guaranteed by the following theorem, saying that if a function f has a relative extreme value fc on an open interval I, then c is actually a critical value of. So because of this theorem, now we actually have the first derivative test for relative extrema. For any continuous function f that has exactly one critical value c in an open interval ab, then f has a relative minimum c if the derivative of f at x is less than 0 on the open interval AC and is positive on the open interval from C to B. And also if now the derivative of f is positive on the open interval from A to C and is negative from on the open interval from C to B, then f has a relative maximum at C. For the other cases, meaning that if the derivative of f has the same sign on both open intervals from A to C and from C to B, then f has neither a relative maximum nor a relative minimum. Or we can say that f has no relative extrema. To help you to easily memorize the first derivative test, the following table is useful. So here we see that if the signs of the derivative of f of x are different over the open interval A from A to C and from C to B, then actually FC is either a relative minimum in case the sign of f of x is minus over AC and plus over CB, and is a relative maximum in case the derivative of f of x has signs plus over AC and minus over CB. And now if the signs of the derivative of f are the same over AC and also over CB, then there is no relative extrema for f over A and B. Now let's try to understand the first derivative test on an explicit example. Let's now consider the case where f of x is the function that we already mentioned just after the introduction. F of x equal x power 4 minus 4 times x power 3 plus 11. So in order to apply the first derivative test, it's natural first to trying to find out what is the derivative of f. In this case, because f is a polynomial function, then we can easily deduce the derivative of f, which is 4 times x power 3 minus 12 times x squared, and then we can factor 4 and then we can let 4 times x squared as a common factor, and then so the derivative of f of x now become 4 times x squared times x minus 3. So for this we know that the 0 of the derivative of f is actually 0 and 3, and it is defined for all real numbers. So it means that we only have two critical values for f at 0 and at 3. So next, now we need to understand the sign of the derivative of f, because we already know the 0 of the derivative of f. So the sign of this derivative can be decided by dividing the real line into three open interval from minus infinity to 0, from 0 to 3, and from 3 to infinity. Okay, so we know that the sign of the derivative of f is actually the same on each of the open interval that we just mentioned. So to actually know the sign of f, the derivative of f, we just need to take any testing value of x on each of the open interval and then evaluate the derivative of f at this point. So say from minus infinity to 0, I choose to compute the derivative of f at x equal minus 1, and you can easily see that this value is negative. This means that the sign of the derivative of f over the interval from minus infinity to 0 is actually minus. And similarly from 0 to 3, I choose to compute the derivative of f at x equal 1, and then I can conclude that the sign of the derivative of f at x is minus. And also from 3 to infinity, Now if you compute the derivative of f at x equals 4, then you get that the sign of the derivative of f at x is actually plus. So from this, now we can easily get the result. So first, from minus infinity to 0, f is decreasing, and it is still decreasing on the open interval from 0 to 3, but actually from 3 to infinity, f is increasing. So the trend from decreasing to increasing here indicates a relative minimum. So for this, we see that the behavior of f is quite easily to understand. It's go from infinity down to 11 as x go from minus infinity to 0, and it's keep on decreasing when x go from 0 to 3, and the value of f as 3 is minus 16. This is actually a relative minimum of f, and after that the function goes all the way up to infinity. So from this, not only we know that minus 16 is a relative minimum, but it's actually an absolute minimum of f. Okay, so that is as far as we can go for now, but actually the graph of these functions look as smoothly as depicted in this picture. So we see that here the graph has complicated concavity, right? There is the part where we see that it's actually look like a parabola that opens up, and also there are some part that actually looks like a parabola that opens down. But if we merely depend on the first derivative of f, then we cannot say anything about these. So that is the reason why we now take a look at the second derivative of f. And before going to concavity, actually the second derivative of f can tells us about relative extrema too. Suppose that in the case that f is differentiable for every x in an open interval from a to b, and there is a critical value c in that interval for which the derivative of f at x equals c is actually 0, then if the second derivative of f at x equals c is positive, then f at x is actually a relative minimum. And in case the second derivative of f at x equals c is negative, then f of c is actually a relative maximum. So let's take a look back at the example that we just studied. Then we already know the derivative of f, then it can help us to easily deduce the second derivative of f, which is now 12 of x times x minus 2. So if we want to apply the second derivative test in this case, we need to know the sign of the second derivative of f, not for all real numbers, but only for the numbers that we care about, meaning that the critical values of f such that the value of the derivative is 0, right? So from this table, we know about the derivative of f, and we see that the critical values are 0 and 3. So for these value, we see that the second derivative of f as x equals 0 is 0, so we cannot apply the second test here. However, for x equals 3, we see that the second derivative of f evaluated at 3 is actually positive. So from the second derivative test, we know that now f of 3, which is minus 16, is actually a relative minimum. Okay, so now let's take a look at concavity and see how we can actually know the concavity of a function f based on the second derivative. Now, intuitively, concave down means that the graph of the function actually looks like a parabola that opens down, right? And concave up is where we see the graph actually does behavior like a parabola that opens up. And for concave down, well, if you consider the tangent line to the graph from left to right, the region where the graph is concave down, then actually you see that the slope of the tangent line is decreasing. Okay, it means that the derivative of f of x is decreasing on this interval. And similarly, when the graph is concave up, then the derivative of f is actually increasing. So for this, we can actually define concavity using the first derivative of the functions. So now suppose that f is a function that we can have the derivative at every point in an open interval I. Then we say that f is concave up on I if the derivative of f is increasing over I, and if the derivative of f is decreasing over I, then we call f concave down. Now we are ready for a test for concavity using the second derivative. It says that if the second derivative of f is positive on an open interval I, or just an interval I, then the graph of f is concave up on that interval. And if in case the second derivative of f is negative on an interval I, then the graph of f is concave down on that interval. And now that we have the definition of concavity, we might also have the definition of points across which the concavity changes. And this is a definition of point of inflection, or also known as inflection point. So for example, in this case, P is actually a point of inflection, because we see that across P, the graph actually changes from concave down to concave up. And we also know that if a function f has a point of inflection, it must occur at a point A where either the second derivative of f at x equal a is 0, or the second derivative of f at x equal a does not exist. Okay, so let's take a look back at the function fx equal x power 4 minus 4 times x power 3 plus 11. So now we are ready to know why the graph of f actually have a fancy look like this, with a smooth shape, and we actually know where it is concave up or where it is concave down, and what are the inflection points of the graph. It is because now we already know everything about the first and the second derivative of f. So we see that now first, when x goes from minus infinity to 0, we see that first the graph, the function is decreasing from infinity all the way down to 11. At 11, we see that the second derivative of at x equals 0, we see that the second derivative of x is 0. And so if we look at the interval from 0 to 2, we also see that f is decreasing from 11 to minus 5. And also we know that on this interval, the second derivative of f is negative. So in this case, we see that from 0 to 2, the graph of f is actually concave down. And from minus infinity to 0, we see that the second derivative of f is positive. So it means that the concavity of the graph from minus infinity to 0 is actually up. So through the point with coordinates 0 and 11, we see that the concavity of the graph changes actually. So it means that the point 0 with coordinate 0, 11 is actually the first inflection point that we can find. And similarly, we see that the point with coordinates 2, minus 5 is actually the second inflection point. These are the only two inflection points of the graph. Okay, because we see that the 0 of the second derivative of f of x are only 0 and 2. Okay, and now we see that from 2 to 3 the function keep on going down from minus 5 to minus 16, and minus 16 is actually the absolute minimum of the graph, and because of that from 3 to infinity the graph goes all the way up to infinity. And so here we also see that the second derivative from 3 to infinity is positive. It means that on this interval then the graph is actually concave up. So for this we can conclude and actually draw the graph of f. Okay, so now let's pause the theoretical part and try to understand why we actually care about all of these by looking at problems that come from real life. It is the problem of maximizing revenue. We're going to see that if we want to maximize revenues, then we're gonna get a mathematical problem of finding relative or absolute extrema of functions. So the problem here that we have is that a stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit in dollars must be given by the function Px equal 1000 minus X. And also the manufacturer determines that the total cost of producing X units is given by the function C of X equal 3000 plus 20X. So based on the price per unit and the total cost, we are asked to find the total revenues Rx, and after that find the total profit P of X. And we want to maximize the profit and actually find the value where the profit get its maximum. And of course we need to know what the price per unit we have to assign in order to get the maximum profit. Okay, so now for the total revenue. We know that the total revenue is actually the number of units times the price per unit. And you know that the number of units is denoted by X and the price per unit is given by the function P of X. So we can easily get that the total revenue of X is actually X times 1000 minus X, which is 1000 times X minus X squared. So this is a function that gives us the total revenue. Now for the total profit, we know that the profit that you get is actually the difference between the total revenue and the total cost. And because you already know the function for total revenue and the function for total cost, then you can easily get the total profits. And in this case is minus X squared plus 980X minus 3000. Okay, so we are done with the task of finding the total profit function. Now it comes to the problem of maximizing profit. So actually we only need to maximize the function Px equal minus X squared plus 980 times X minus 3000 over the interval from 0 to infinity, of course, because the number of selling item is actually positive, right? So to do so, we might use the first derivative test or the second derivative test based on the situation that we get. Anyway, first thing first, we need to compute the derivative of the function P. because it is a quadratic function, polynomial function, so the derivative of p is quite easily to get, and by now it is not surprising that you can get it easily, and it is given by minus 2 times x plus 980. So because of that, we see that px has only one critical values at x equal 490, and for this reason we might actually want to apply the second derivative test, in this case by computing the second derivative of p, which is quite easily get by p double prime of x equal minus 2, which is always negative. So using the second derivative test, now we see that the value p490 is actually the unique relative maximum of p of x, and of course because of that we know that it is the maximum profit that we can get, and by computing p of 490 we know that it is $237,000. And because we know that after selling 490 items, we can get the maximum profits. So by using the formula for the price per unit, we can easily get that the price per unit needed to make the maximum profit is P of 490, which is $510. So from this example, we know that maximum profit occurs at those x values for which the derivative of x is 0, and the second derivative of p is negative. But you know that the profit function p is actually the difference between the revenue and the cost functions. So by rephrasing this, we get a very useful remark that the maximum profit occurs at those x values for which the first derivative of the revenue is the same as the first derivative of the cost, and the second derivative of the revenues is actually less than that of the cost. And also based on the example, now we can have the maximum minimum principle 1, saying that if f is a continuous function defined over a closed interval from a to b, then we can find the absolute maximum and minimum values over a and b following these steps. The first step is that we need to find the derivative of f. The second thing is to determine all critical values c in the closed interval from a to b and list them. Let me remind you that a critical value c is a value such that the derivative of x of f at x equals c is either 0 or does not exist. And the next step should be listing all the values that we found from step 2, adding the two nth point a and b. And after this, we need to evaluate f for each value that we already found here in step 3. And now we can conclude. The largest of these is the absolute maximum of f over the closed interval from a to b, and the smallest of these is the absolute minimum of f over the open interval from a to b. And we can actually modify this principle to get things done not only on a closed interval from a to b, but also from open interval from a to b. You only need to remove the endpoints a and b from every step that you see here. Only that there is no, if you consider the case over an open interval from a to b, there is no guarantee that the absolute maximum or the absolute minimum exists for f over the open interval from a to b. So you need to be careful about that. And also we get the principle 2, saying that when there is only one critical value c in an interval I, we actually might not need to check endpoint values to determine whether the function has an absolute maximum or minimum value at that point or not, thanks to the following result saying that if f is such that the derivative of f exists for every x in an interval I, and there is exactly one value c in I for which the derivative of f at x equals c is 0, then we know that the value of f at c is the absolute minimum value over I if the second derivative of f at x equals c is negative, and if the second derivative of f at x equals c is positive, then fc is actually the absolute minimum value that we are looking for. Okay, so after a short theoretical part, now we're back with useful example to see why we actually need to care about maximizing functions or minimizing functions. So what we're now looking at is a problem of maximizing the volume of a box made from a piece of paper just by cutting the 4 corners by 4 same square and then fold off the flap. So in this example, we choose the piece of paper of the size 20 by 25 centimeters. And in order to maximizing the resulting the volume of the resulting box, let's take a look at the picture that we depicted here. So we see that in order to create a box from the paper, then we need to cut off from the 4 corners of the paper 4 same square. Let's denote the sign of such squares by x. Then we know that the resulting box will have 3 adjacent signs as x, 20 minus 2x, and 25 minus 2x, right? So based on the formula to compute the volume of a box, we see that the volume that we denoted by v of x is actually the product of x, 20 minus x, and 25 minus 2x. From the nature of x, we know that x, 20 minus 2 times x, and 25 minus 2 times x are all positive because they are signed of a box, right? And from this we deduce that x should be positive and less than 10. So the problem of maximizing the volume of the box is actually the mathematical problem of maximizing the function Vx over the interval from 0 to 10. Okay, so that's the first example that we have here. The second one is the problem of minimizing material needed to make food storage containers in a cylinder shape. And we need that the can to have a volume of 500 millimeters. So we are asked to find the dimension, meaning the height and the radius of the cylinder, that will minimize the material needed to produce the can. Okay, so we see that if we unfold the can, then we see that the material needed to make that can is actually the material needed to create two circle, that is the top and the bottom of the can, and also the rectangle that made up the wall of the cylinder. So let's denote h the height of the can, and r the radius of the top as well as the bottom of the can. So we see that the total surface area A needed to make the can is computed easily as follows. So it is the sum of areas of the circle and the sum of the rectangles, right? because the radius of the circle is r, then the area of that circle is pi times r squared. We are left with computing the area of the rectangles. Now, one side of the rectangle is actually the perimeters of the circle with radius r, so it can be easily seen to be 2 pi times r. But what about the height, which give us the other length, the other side of the rectangles? It can be easily deduced based on the fact that the volume that we need is actually a fixed constant of 500 millimeters. And we know that it is h times pi times r squared, so h is actually 500 over pi times r squared. So for this, we know that the area needed, the area of the material needed to make the can is computed as the function of 2 pi times r squared plus 1000 over r. And actually we know that the radius should be positive, right? So that is actually the problem of minimizing the function ar there over the interval from 0 to infinity. So that's the second example that we have. And the last example that we want to introduce is from business. Well, there's a problem of determining a ticket's price in order to maximize the total revenue. So the information that we have here is that we know that with an admission price of $26, it averages 1,000 people in attendance. And now if we drop $1, every dollar that we drops from the admission price, we gains an extra of 50 customers. And in general, each customer spends an average of $4 on concessions. So we are asked to find the admission price to maximize the total revenue. Okay, that makes sense. So now denotes X the number in dollars by which the price of admission $26 should be decreased. And note that if X is negative, then actually we can increase the price. So because every dropping dollars will increase 50 customer in extra, then we know that the increase in ticket sales is 50 times X when the price drops X dollars. So the total revenue is given by the revenue from tickets plus the revenue from concessions. The revenue from tickets is computed as the number of people times the ticket price, and the revenue from concessions is given by the product between number of people times the average money that they spend on concession, that is 4 in this case. So we can easily see that the revenue, the total revenue, is given by minus 50 times X squared plus 500 times X plus 30,000. Okay, so this is now the problem of maximizing the function minus 50x squared plus 500x plus 30,000 over the interval from minus infinity to 26. Why we stop at 26? Because if x get bigger, greater than 26, then actually the admission price should be 0. Then we do not have anything at all. Okay, so to review, from these 3 examples, we get 3 mathematical problems maximizing 3 different functions. So in order to review what we've already done so far by applying the theoretical part in practice, so now I will choose to solve one of these problems and leave the rest for you as exercises, because they should be treated similarly. So of these three examples, the second one should be of interest because it involves the rational functions. So let me choose to solve the second problems and leave the first and the third for you. Now we have the problem of minimizing 2 pi times r squared plus 1000 over r over the open interval from 0 to infinity. So the first thing we need to do is to find the derivative of a, and by now you should be doing that very easily and get the result of 4 pi times r minus 1000 over r squared. So next we set the derivative to 0 and find critical values. So based on the formula for the derivative of a and together with the condition that r is positive, we see that 4 pi times r cube is actually 1000. It means that r is approximately 4.3, and you can easily get using a numerical calculator. So next we might think about the second derivative test by computing the second derivative of a at that critical values. So the general formula for the second derivative of a is actually 4 times pi plus 2000 over r cubed. So because of that, we can easily see that the second derivative of a evaluated at x equals 4.3 is actually positive. It means that following from the second derivative test, then a of 4.3, which is approximately 348.68, is actually the absolute minimum value of AR that we are looking for. So that is the answer for the problem of minimizing AR.